Let's talk about the first part of chapter 3. So we've been talking about the ones in chapter 1 and 2. It was merely good review over Jenkins 1 and 2 chemistry. So maybe from chapter 3, we can say we are actually hitting on the actual real organic chemistry. Okay? So it starts with the nomenclature, but in chapter 3, we're going to focus on alkane. So alkane simply means there's organic compounds, obviously carbon and hydrogen, sort of thing, but they all be linked in a single bonding. Okay, so there's no double bond or triple bond, but only the ones with the single bonds that we're gonna focus on chapter 3 and this chapter. Okay, so. So this ane actually means they're only single bond. So we're gonna just learn about how to name those alkane compounds and so forth by just looking at this structure. So if that is the case, before we move on to the nomenclature, we slightly did it like a last lecture, but we just want to know why it's so important first. Okay, so say we have some. I'll just write it here. This doesn't write down. But so if you think about the isomerism, or just the relationship between those isomers. So you guys remember the isomers, right? So the isomer simply means they actually share the same chemical formula. Okay, but they're still different compounds to each other. Okay, so meaning even though two compounds share the same chemical formula, they're not always the same compounds, because it could be different in a structure or chemical bonding and so forth. Okay, so this is just the basic idea about the isomerism. Whenever they share the same chemical formula, if they're still different compounds, how are we going to distinguish them from one another? Okay, so the first way to do this is looking at the structure. So mainly it gets into the two categories. Okay, so the first one is the structural isomer. Okay, the other one is what we call stereo isomer. Okay, isomer. Okay. So in this case, we're gonna focus on this one. Okay, so this is what. So we know they share the same chemical formula. Okay, the same chemical formula, but they share different bondings. Okay? And now you guys wonder, what do you mean by different bonding? We all said maybe alkane we share only single bonding. Okay? So what I mean by the different bondings means between which carbon to which carbon. So I'm going to show you the one example. So meaning the stereoisomers, we're going to cover this one soon later this semester. It has the same chemical formula, but also the same bondings as well between each different carbons too. But sometimes still they cannot be the same compounds, either when you look at the optimal isomers, geometrical isomers, and then also other types of the diester isomers. But we'll cover this one later. Okay. So, but the difference between these two is either they're going to share the same bonding or different bonding here. And now you guys wonder again, what do you mean by different bonding here? So here's the thing. If I draw the structure, looks like this. Okay? You see this one over here, hopefully I assume that you now see they're only like lines and everything, but you assume there's 5 carbons, right? And there are 3 hydrogen, 2, 2, 2, and 3. Because the carbon should have, if they're all single bond, has to be 4 bonds each carbon over here. But anyway, you see this now, right? Okay, for sure. So I'm not gonna do this every time, because we normally use the skeleton structure for most of the organic chemical reactions. Anyway, so if you have a looks like something like this one, you can have this one too. Okay, you can have this one. Okay, so the thing is they're all made of 5 carbons. Okay, and if you do the counting the hydrogen on each carbon, they're all same too. Doesn't so as long as they're all single bond, if you count, there's 3 hydrogen, right? 2, 2, 2, 3. So it'll be you guys know this, right? So obviously it would be just 12. You don't even have to count it, but you can count it too. So if you do the same, 3, 2, 1, 3, 3. Okay, this is 12 too. This is the same. So they share the same chemical formula here, right? This is 3, 3. The same chemical formula here, but structurally different. Okay, and what I mean by the different bonding means you need to number the carbon. So they all single bond, I know, but if we number the carbon, 1, 2, 3, 4, 5, you know, there is this carbon will have only 1 bond to the number 2 carbon here. And this one will have a 2, 2, 2, and 1. Okay? If you look at this one over here, this carbon has only 1 bond to the carbon 2. Oh, I just numbered it. So if you number this one to this way, well, this way. Okay? Then you have a 1. Number 1 carbon has only 1 bond, 1 single bond to the carbon 2, but carbon 3 has 3 in the middle, and 4 has only 1, 5 only has 1, 2 has 2. Okay? So for individual carbons in different structure isomers, they show different numbers of single bonds. So that's why they show you different structure. Okay? So we call them structural isomer or constitutional isomers. They're meaning the same thing. If that compound, even though it has the same chemical formula, if it's structurally different, meaning they're absolute. So the physical property of those are different because if their structure is different, they also change the physical property as well. So it's fundamentally, constitutionally different. The structure almost tells you almost everything about physical property of the compound. If you see the change in the structure a lot, even though they share the same chemical formula, they may show quite different physical property because of that. Okay? So stereoisomers, some, but this is the kind of main idea that we're doing, especially for the alkane, because they're only going to be different in structure. Okay? Makes sense, right? Okay, good. All right, so how is it so different in the physical property? So one of the example is the boiling point. And the melting points. So I hope you guys remember the intermolecular force I have discussed in the last lecture. This simply means how they're going to share how much strong interaction among the molecule. That's what was about the intermolecular force. So intermolecular force is highly related to those two. Okay? So here's the thing. If there is a force between those two molecules over here. Okay, maybe this is one molecule, another molecule here. Okay? If they share the strong interaction or strong force, you can say. These two molecules experience very strong, like tight, like bonding-like interaction. They kind of like to each other. Then means you're going to have this molecule will have higher boiling points and also higher melting points. That's what it means. So intermolecular force is crucial for those two measurements, those two physical properties, because this will determine how high or how low boiling points or the melting points those molecules will show you. Okay, because this one, let's think about the temperature first. Okay, what is the temperature, by the way? What was it again?
Kinetic energy.
Kinetic energy, good. Good. That's very good start. Okay. Kinetic energy. But this kinetic energy coming from where? That's very good start, by the way. That's very good answer. This kinetic energy coming from, especially when you think about the temperature, heat, right? So temperature simply means transformable kinetic energy to the matter. But temperature will measure how much heat do we have per unit volume. So if there's a lot of heat energy concentrated in this space, if you measure the temperature, it will be very high. Because the heat energy per unit volume will be so high, so we show you high number in temperature. So temperature is simply measuring what? Not just the heat energy, but per the certain space. Makes sense, right? So if those two molecules are strongly bound to each other, meaning strongly interacting each other, you need to have higher kinetic energy to make them break apart. So if they're stable, they're not going to break apart, because why would they just break apart? They don't have energy to do so. But if you put a lot of heat energy, that transforms into kinetic energy for those two. So if they're strongly bound together, you need to have a more heat energy to break apart. Meaning you need to have a higher temperature for those molecules in that area. So if these two have a strong strong force there, you're going to have a higher boiling or melting points. If those forces are very weak, okay, very weak, you're going to have a lower boiling points and lower melting points. Okay. Make sense, right? Yeah, perfect. So if that is the case, let's look at this one in the structure-wise. I just told you this is also same in chemical formula, but only structurally different, right? Okay. So if this is the case, whenever it's in the same chemical formula, they have also obviously same molecular weight too. Okay? So they all share the same molecular weight, same chemical formula, but just different in structure because different bonding for individual carbon here. If that is more linear shape, we'll have a higher boiling points or melting points, you can say. You have a more of like a less linear shape. We normally call those type of shape bulky. If it's more bulkier, okay? If it's more bulkier, it tends to have a lower boiling points. Meaning, this one will have a stronger interactions to another. This one have a less because of its structure. So if you look at this one on the other molecule, so once again, when we talk about the boiling points and melting points, you need to think of the intermolecular force, meaning you can just see this one from the one compound, but another one. So let's try to put another one here on the top. Then as you can see, most of the parts of the compounds are interacting onto another molecule in this one. So it has more room for them to interact well with another same molecule, right? But if you have a bulkier compounds coming into the neighbor molecule, they only have a certain limited space where they can do the interactions there. So that is why they're going to have a weaker interaction than this one because of its structure. So eventually this will bring up to the higher boiling points than this one. So it's all relative term that you can find out by just looking at the structure of the alkane compounds. Okay? Makes sense, right?
Dr. Cho,
Yeah.
what is the MW?
This is molecular weight.
Okay.
Molecular, because if they show the same chemical formula, there has to be same in also like molecular weight. Right? So that is the one thing I want you to remember. This will be on the exam, okay? So if it's more linear, they'll show you the higher boiling points or higher melting points. If it's more bulkier, I will show you lower boiling points and melting points. There's one more thing that I want you to remember for the exam and the quiz, is the size also matter. So when you try to look at the, if you took my Genchem 1, you already got this knowledge before. If you think about the two boxes are there, and this box is filled with the metal beads, metal chunks, and this box is filled with the feather from the birds. Okay. If you try to take a blow on the top of these two boxes, obviously the metal beads will stay the same because it's heavy, but the feather is just so light. Even the very slight, flow of the air will just make it flow into the air, right? Because they're so light. This is a quite extreme analogy that I'm applying to the compounds. That means that if you have a higher molecular weight of the compounds, you're also going to have higher boiling points because it's simply heavier. So it takes more of the interactions, kind of focus on the molecules. So you need to have more energy to make it go into the air in the gas phase. But if it's lighter, if it's not so big, a small molecule will tend to have low boiling points because of that. So only two factors will determine your boiling points and melting points, physical property of the compounds. The first one is molecular weight, and second one is how they can interact to each other based on their shape. Yeah. So these two things is only ones that I want you to remember for the physical property of the compounds. They should be good. Okay. Does it make sense? It's kind of pretty. Yeah. Alrighty. So this we're going to the exam. Okay. Please remember them. Okay. Maybe I can say in the exam what might be the two things that will determine your boiling points and melting points of the compound. You need to say molecular weight and the shape. Okay, that's all. Okay. Linear shape. All right, so we know why it's so important to find out what's the structure, and then obviously the next step we need to do is how we're gonna present to the others, meaning nomenclature. Okay, so once again, we're gonna follow the four main parts of the name, locans, right? You guys remember this one. This is the prefix, base, and suffix. So I'm going to start with the base because this is very highly related to the nomenclature. So because the base will tell you how many carbons how many carbons in your longest longest carbon chain. And then any other carbon or the functional groups attached to, well, not functional groups, the alkyl groups, or to the carbon chain, we call them prefix. So I'm going to show you some example. But if there's other small groups attached to your longest possible carbon chain, we're going to call them prefix. It's like a peripheral parts of your compound. And locant simply means it's just locating where those are attached to the base of your carbon chain. And the suffix just means in chapter 3, just A and E, because it indicates all the carbons in the carbon chain are all single bonded. Okay, so
Does
not.
that say one? What is A and E? What does that say?
Oh, A and E means it's like arcane, right? So all carbons in the carbon chain will be all single bonded. No double bond, no triple bond, just all single bond. Okay? So this will make quite easier to make some names for the compounds. We'll do the double and triple bond in next chapter. So don't worry about it. But for now, we're gonna focus on the ones that only has single bonds, meaning it always going to have A and E at the end. Okay. Any other questions? Good. Perfect. So if that is the case, I'll definitely show you some example here. So I just once again, this is the kind of thing I want you to remember. Okay. So 1, 2, 3. 1, 2, 3. But is 4. Okay. Pent is 5. Hex is 6. Hept is 7. And oct is 8. None is 9. Bit is 10. Okay. So once again, you don't have to know more than 10. We know we have undedecan, dodecan, icosane, aconsane, and everything. It means like 10, 20, 30, 40 carbons that we're not gonna do. So the only thing you have to do is 10 to, I want to say 1 to 10. Okay. So just remember this one. I'll keep this one over here. Okay. And I'll show you one example over here. So let's just start with the very simple ones. Okay. We can start with the this the linear simple alkane over here. So once again, it means we have carbons in here in each corner and the dots at the end. So we have 5 carbons over here. So meaning it has the 5 carbon is mean pent. And this is also our longest carbon chain. This is our longest carbon chain. There's no other scenario you can make longer than 5 because it's just linear. Okay. So if that is the case, there is no.
So there's no linear hexane or anything above 5?
Mm-hmm. Yeah, if it's well, I'm sorry, what was that again?
No. So you're saying that if it's linear, it'll never be more than 5 carbon atoms, or? Okay.
Oh, so whenever you try to find the longest carbon chain, you count the carbon 1, 2, 3, 4, and 5, right? Then you go for a 5. That means your base is your. So those are names for base.
But you said it would never be more than 5. That's what confused me.
Oh, just 5.
Never mind.
Okay. So if it's 4, obviously we built, not 10. So you just go by numbers. So this is actually means how many carbons in your base that will take that name on each. Okay, makes sense, right? Okay. So that means they have 5 carbons in the long carbon chain. So we just bring this 10 as your base. Okay, this is your base. And if you look at this one over here, there's no additional groups attached to this one. There's no additional group there. So there's no prefix, meaning there's no locant there. Because locant is simply meaning where there's a prefix on. So we don't have to worry about the locant and the prefix now. But now, like I said, they're all single bonded, right? So we're gonna put A and E at the end. So it's just hinting, that's it. So this is quite easy to name because they don't have a prefix or locon or anything. Okay? So to make it very clear, if we have instead of 5, 6, 1 might be the name. Okay, so there is 1, 2, 3, 4, 5, 6, right? So this is also, there's no additional group. This is only one possible carbon chain you can have. And this is also longest too. Then you find this one, right? Hex. And then you put A and E because they're all single bonded. It's a hexane. Makes sense, right? It's pretty easy, right? So then, how about I know you guys already got it. I just want to make sure. How about this one? So it's 1, 2, 3. So what might be the name of this one? Propane. Perfect. That's it. Really. Okay. So we got how we can do the base and suffix, which is quite easy job to do with the alkenes. Okay. So that means how about we have some additional group on it? Okay. So there's one thing also I need to mention before I went over there. So whenever it's an alkane, like I said, this is some sort of a organic compounds. They're all bonded in single bond. If there's any additional group attached to it, we're gonna call them alkyl groups. Okay. So instead of we putting A and E, there's an additional group. We're gonna put Y and L instead. Okay. That's the thing you need to just know before we move on. So alkane is your compound name, but if there's any additional group attached to it, to the base, we're just gonna put YL instead of A and E for that group. So let me show you one example here. So if you have pentane again, we have pentane again here. Well, I put this one carbon group over there. Okay, so I don't show you here, but you know that is CH3. Because this is the one carbon there attached to your base. Okay, this is base. Here's the thing. This is your base because if you can also do 1, 2, 3, 4. There's another scenario too, the carbon chain. But I'm gonna choose this one as my base because this is longer than this line. So if you go this 1, 2, 3, 4. There's 4 carbons in this chain. If you do 1, 2, 3, 4, 5, there's 5 carbons in this chain. So instead of we choosing this one, I'm gonna choose this one as our base. So this will be still pentane, right? Then that makes once you find out your longest possible carbon chain, now you can tell which one is your alkyl group, which means additional prefix is just this one, right? Only additional thing to your base is this one, right? And same here. If that is, so just separate them for moments from the base. If you look at just this one over here, it only has 1 carbon, which is meth, right? So if that is the meth, this is only 1 carbon attached to this one, so we can do this with the meth, right? And once again, if it's an additional group, we put not A and E, YL. Okay? So this become methyl, or some people pronounce it methyl. I don't know. It's whatever is better for you to pronounce. But it has methyl group over here. And then you just need to put, so this is your prefix now, right? Now you find your prefix. So prefix can be only found once you find the longest carbon chain. So always, the first thing what you need to do when you try to name the compound is finding your base, longest carbon chain. That's the only thing, the first thing you need to do. Then next you can find the prefix. So we find it over here. So now it becomes methyl pentane. So now just we need to fill the locon here. So for locon here, you just need to name it, number the carbon in your base. So it'll be 1, 2, 3, 4, and 5. Okay? So it doesn't matter. If you count the carbon from here, it still be 1, 2, 3, 4, 5. So no matter what, you're going to have 3 carbons on number 3 carbon, this is where you have a methyl group. You just need to put 3 there then. 3 hyphen dash methyl pentane is that one. Okay?
Can you explain that one more time?
Yeah,
Yeah.
yeah. So the base is so important because this is where you can find the longest carbon chain. So now you got the pentane. And also once you got the longest carbon chain, you got the additional group attached to, which is 1 carbon. So we still use the same nomenclature for the additional group that is also meth, because there's only 1 carbon there, right? So we're gonna put, it's like a methane, but we're not gonna do methane because it's a alkyl group, so we put YL instead. So it makes methyl. Okay? So, but we know
Wait, why don't we use ane? Can you just
because
repeat
this
that
is
one?
not a base. This is not a base. This is an additional group attached to the base.
Okay.
Yeah. So if there is an additional group attached to your base, we call them alkyl groups. So this is why we're using different name for it, which is YL. So it's not methane propane, it will be methyl propane.
Oh, I just need the,
pentane.
like, where you got the 3 from, I need that.
Oh, 3, yeah. This, I know this is kind of the confusing because the when you find the base, you only need to find the either go from the other end. So you have a chain. If you have a chain, the only decision you need to make is 1 or 2. Either you go from left to the right or right to the left, right? Either you cannot count just 1, 2, 3, 4, 5. No, this is not a good way to number because you have to do it sequential way, right? So only thing you can do is 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. This is the only way you can do because it's literally line. Yeah.
How would you number it if
Mm.
they're like an even number of carbons? Like, because you
Mm.
said for that one you could go from either direction and
Yeah.
still get 3. So, like,
Mhm.
how would you do it if it was like butane or?
Yeah, so that's a really good question. So this is where I'm going to next. What was it?
Okay, so
Uh-huh.
the 3 is where it's attached at the base? Is
Yeah.
that- Okay.
The when you number the carbon, 1, 2, 3, 4, 5. So you can call them like this is number 1 carbon, number 2, number 3, but that group is attached to your number 3, right? That's why we put number 3 over there.
Gotcha.
So the locon actually means where your additional group is, which is your methyl group on where in pentane.
Gotcha.
Okay. Yeah.
If it was on like 2,
Uh-huh. Perfect.
would-
Yeah.
so if you counted like 1, 2, 3, 4, 5, like
Mhm.
could it
Perfect.
be like
So,
4 or 2?
that's-
You know?
That's really good question. So I did this one first because I don't want to confuse you for this one already. But if that is the case, this is the next one I'm gonna do. See, how about we put here, right? We put here, right? Okay. So in this way, you have to count it from left to the right because the 1, 2, 3, 4, 5. Or you can do 1, 2, 3, 4, 5. Then there's a 2 possible scenario. Either you can say this is the 2-methyl, or you can say 4-methyl. Okay? Because it's either you have 2 or 4. It depends on where you count the carbon from, either from left or the right. Then in this case, you always going to follow the lower one. So in this case, you know where you should count the carbon from is left. So for example, if it was maybe other compounds, okay, this is octane, right? There's 8 carbons, right? So if I put it maybe here, okay, here, okay. So here's the thing. I'm gonna count the carbon from 1, 2, 3, 4, 5, 6, 7, 8. Okay. Then you have a 1 methyl group on 4. But if you count it from 1, 2, 3, 4, 5, 6, 7, 8, you have a 5 carbon that has the methyl group. So in this case, it is going to be 4 methyl octane or 5 methyl octane. Will be 4. So that's why in this case you have to count the carbon from left to the right. Because you need to always give the lowest possible number for the locant. That's the job. That would you guys doing really good. Do you guys know why? Because you cannot ask this question if you didn't understand what I've been taking today.
So it's always
that
the
was
lowest
really
number?
great. Yeah.
It's always the lowest number.
Always lowest number.
Okay.
Always lowest number. So if I change this one to here, it's not going to be 6 methyl octane, but it will be 3. Perfect. There you go. That's yeah. Go ahead.
So if you count from the left, you'll always get the lowest number?
Always go. So if I put the number here, right? Then you have to count the number carbon from here to make this local number lower than the other. Yeah, perfect. That's it. You guys doing so great so far.
Will there be like chains where it's more than just one carbon
Mhm.
chained off?
Sure. Yeah.
Okay.
Absolutely. We do have them. So let's do one more. I don't want to tell you a lot today because we still have quite a time. So let's do a bit more. Okay. How about this one? I'm just gonna give you this one. So if you have more than one alkyl groups, what should I do? Here's the thing. The first of all, you just need to find the longest carbon chain anyway, okay? Which is this one. This is the only one longest possible carbon chain you can find from this compound over here. But the problem is now you have 2 methyl group here instead of 1. And can you guys tell me possibly where we should the number carbon from, like a left or right? Left, perfect. Yeah, so that's great. 1, 2, 3, 4, 5, 6. So it can have instead of 1, 4, 5, we'll have a 2, 3. So 2, 3 still lower number combination than 4, 5. Okay, so that's perfect, great. So if that is the case, it's actually pretty simple. It's not really, I don't think it's really difficult. So longest carbon chain is still 6. Even though there is 8 carbon, it's not going to be octane because we only count the carbon in the longest chain. So it's not octane, but hexane, okay? Because it's only 6, right? So the hexane, so hex is your base, and ane is your suffix. Will be same for the chapter 3. And then you have just number this one. So this is also same. Whenever you put the local name here, okay, and you have methyl groups over here, but you have on carbon 2 and 3. So do not do this one, okay? You always also when you put the 2 numbers now, you have to put 2 and 3. So always the lower number first and the bigger number next, okay? And you do hyphen dash over there, okay? And there's only one more thing I want you to know. That is, you have to put di. Di means 2. So that's why you have 2 numbers for the locants, because there's a 2. There might be 2 additional group attached to it. So if that is the case, you can say either 2, 3. That is for each methyl group, but also di means is 2. So you don't have to do this when it's 1, which is mono, but you don't have to do that. You only need to do di, tri, tetra, quanta, and penta, and so on. Okay, but until then, I'm sorry, the tetra and penta. So, but depends on how many additional group attached to the base. You can say either, once again, di, tri, tetra, penta, and so on. Okay, but just make sure you also put that numbers of the locant. Yeah.
So you know how you said the methyl
Mhm.
depends on how many carbons are on the chain, like connected, like.
Yeah. So how many
What if
carbons
it-
in that chain? Yes.
What if it's more than 1 carbon?
Yeah, this is what we're gonna do next week. You wanna do it today? We have 1 minute. It's the same. No? It's the same. So whenever you have more than 1, maybe more than 2, right? Okay, 2. Same. There are 2 carbon is S, right? And this is the additional group, so we put what? Ethyl. That's it. That's it. And whenever you have an ethyl and methyl group here, you order them by alphabetical order, which is E comes first, then M in alphabetical order. So you put this group first, and the methyl group, I'll do this next one. Yeah, we still the way to go, but you guys did so far so great, okay? All right, so let's have time for